All right. So we're starting. This is out of the set that I have. This is the one labeled 1. So this is the one labeled batch 1. All right. Which abstract data type best described as a first in, first out structure? Which one is best described as a first in, first out structure? Anybody wants to offer the answers?
This will be too hard.
First in, first out. The answer, thank you, Cherise. It's a Q. Right, so the answer is Q. The QADT abstract data type operation NQX adds the element X to the front of a Q, adds the element X to the rear of a Q, adds the element X to any free position, or removes the element X from a Q. Which one does it do? The QADT NQ operation. It adds element X to the rear of a Q. Because how Qs work, right, answer Alexa? How Qs work is that Qs add elements to the rear and it removes elements from the front. So if the elements P, T, S, R, and Q are added to a Q in that order and then removed one at a time, in what order would they be removed? If it is first in, first out, then the first in was P and the last in was Q, right? And it goes in the order. So P, T, S, R, and Q in the same order. Mount Holyoke High School has one computer lab with 10 computers and one printer fully networked. What abstract data type would be best suited to handle the print jobs of the student? When you come to a print job, it's first come, first serve. So sending jobs to a printer will be the best one would be to have a print queue. A stack contains the elements W, X, Y, and Z as shown below. Which of the following would be the contents of the stack after 2 elements were removed and element R was inserted? So we have to remove 2 elements. We always remove from the top. So if it is that we have in a stack W, X, Y, and Z, and we pop 2 elements off the top, we're taking off W and X, and then you insert an element R, you will end up with R, Y, and Z. So the answer here is B. R, Y, and Z. Which of the following is true for both a linear search and a binary search? Right? For both a linear search and a binary search. Okay? Just to remind you guys how these 2 searches work, a linear search, if I have 9, 7, 3, 2, 1, 4, 8, and a binary search, in a binary search, the list must be ordered. So I'll have to have 1, 2, 3, 4, 5, 7, 8, 9. Okay, so for the binary, my list must be ordered. In the linear search, the list doesn't have to be ordered. On average, they search half the list, right? A linear search could search here, or it could search the whole list, right? Or it could search to half the list, but it depends on the size of the list and the key, whether or not the value exists in that list. So if the value doesn't exist for a linear search, it must search the whole list. Okay, it must search the whole list. So that on average it searches half the list is truer for the binary search, which always cuts the list in half and then goes down from there. But for the linear search, you don't know if the value is in the list or not in the list. And if the value is in the list, or if it's not in the list, or if it's closer to the end, on most occasions, you're going to have to search further in the list. So A is not the most appropriate there. B, in the worst case scenario, they search the entire list. No, binary search never searches the entire list. Okay, so that's not true. That's true for the linear search, okay, where you have to go through every element in the list. But the binary search, it will always look for that middle value and go either to the first half or the second half of the list if it doesn't match the middle value. They can be used for searching an ordered list. This one seems true for both. You could search an unordered list or an ordered list with linear. You could search an ordered list only with binary, right? And D, they require that the list be ordered. The linear search does not require that the list be ordered, but it can search an ordered list. So C is the most appropriate answer here. It's true for both of them, okay? Which of the following specifications of a set of data and the set of operations that could be performed on the data? A set of operations and the set of operations and the set of data itself together, right, is an abstract data type. Okay, remember what makes an abstract data type different from a regular data type is that the data inside of an abstract data type has operations associated with it or functions associated with it that will allow for data to be added and removed. Okay, so where we have the linked list, we have insert to insert a new node or remove to remove a node, right? In terms of a stack or a queue, you have push and pop or enqueue and dequeue, and you also have is full or is empty. And those are operations. You can't put data into a stack or queue without using these operations. All right, you can't put data into a stack or queue without using these operations. So we have some code here, and it's an algorithm for a linear search, right? It's a linear search, and a linear search we know, as we just spoke about, right? I'm going through it so that we could just simply quickly remember. Your linear search, if you have values, and you have a search key, right? It will compare that key against every value until the key is found and the location where that key was found is returned. Or if the key doesn't exist, it searches right until the end, and then it sees that a flag saying found didn't change, so it tells me that it was not found. Okay, so we know that when we find that, we find the value, we have to change the flag, right, that says found to be true. Okay, so let's take a look at the code. We have count being 0. Count could tell us, of course, the position of the element, right? Flag is equal to false because we have not found the value yet. We say repeat if list at position count is equal to target. So target is our key value. Then what do we want to do? Right? We want to do something and then end if, and then we do something else until flag is equal to true or some other condition. And if flag is equal to false, then this last one will tell us what happened, something here. So this last one here is obviously saying that target is not found. Okay, so in all, Once the flag is equal to false after we finish search, then we know that the target is not found. So then that rules out B and that rules out C. Because if it is that you started off with the flag as false and it wasn't found at the beginning, if you still have the flag as false as the end, then that means that you didn't find something. So the answer is now slimmed down to A or D. All right. So if the list at position count is equal to target, which means that if the value was found, then we want to change the flag to true. In both A and D, the flag is true. So both of these are fine right here. So far we know that this is good, this is good, this is good, and this is good. All right. Then we say for position 2, we want to add 1 to count so that the next time that we loop, right? The next time that we loop, the next time that we loop, the list will be looked at. The list position that we looked at is at the next position. So we add 1 to count. In both of them, we have add 1 to count. Now, notice that we started count at position 0, but the list size is size n. The list size is size n. So what do we want to do with an array list at size n? If an array list is size n, if I have an array 1, 2, 3, 4, 5, and I have position 0, 1, 2, 3, and 4, the size of my array n is equal to 5 here, right? Which means that if I want to go to the last position, right, then it's at position 4, right? Sorry, the last position I want to be able to search is position 4. So the first time I check count is 0, then I carry count up to 1, and I say until flag is equal to true, or n is equal to what? N has to be equal to size n, sorry, or count is equal to size, right? Because otherwise, if I look, this is a repeat until loop. So it's checking. I have to be able to check position 2, position 3, and position 4. And only when I increment this to position 5, which is not a searchable position, right? There is no position 5. So this is count here. This is count here. We have to be able to count these positions. But only when count is the same as n should we stop. So the value that we're looking at here is, the answer that we're looking at here is D, because we have to stop when count is equal to n. Do you all understand how I got this? You all understand how I rationalize that, right? Nobody's saying anything. Yes?
Yes,
all right,
sir.
yes. All right, good. Thank you. So we have the following list: frog, ant, dog, grasshopper, bee, fish, and snake. Which of the following lists will not be applied at any point while applying a selection sort algorithm? If we have a selection sort algorithm, and we have, let's say we have ant, let's just put an A. Dog is D, grasshopper is G, bee is B, right? Ant, dog, grasshopper, bee, fish, snake. Bee, fish, and snake. How does the selection sort algorithm work? The selection sort algorithm looks for the smallest value, or it marks the current value as the smallest value, and then it looks ahead to see if any values are smaller than current value. And if it is, it marks it and continues searching, looking for an even smaller value. At the end, it takes the known smallest value and it swaps it with the current value. That makes sense? So we'll see it in action here. So far, right, I'm going to put it in a different color. We have the current value and the smallest value here. And we search A against D, A against G, A against B, A against F, and A against F. None of them are smaller than A. So the first thing that we'll end up getting is A, D, G, B, F, and S, right? And then we move on to having our current value as D and the smallest value as D. Now we know that A is already smaller. We only look forward. So we compare D and G, compare D and B. And what do we see with D and B? D and B, we can mark B as a smaller value. Then we compare B and F, B and S. And what will happen here is that we've reached the end and we have to swap B and D because the current value and the smallest value are different now. So we end up with A, B, G, D, F, S. G becomes the current, G becomes the smallest. G is compared against D, D is smaller than G, so D is marked as the smallest. D and F, F comes after D, D and S comes after D. So we've reached the end. We have A, B, D, G, F, S. G is now looked at as the current and the smallest, right? We compare G and F. F is smaller than G, so we mark F as the smallest. We mark F as the smallest, and we compare F and S is not smaller than G. So we have to swap F and G, right? So, we had two Fs. Ant, dog, grasshopper, bee, fish, snake. Right? Ant, frog. Oh, I didn't notice frog inside it. Sorry. Right? So we have F. I totally did not notice the word frog there. Right? But at this point, frog should not have been affected anyway. So I'll just stick in FR here, right? Which is oh no, we had frog here, so I have to start over. I'm sorry. Yeah, I have to start over because frog was first. I don't know how I missed the word frog, and nobody said anything up until this point. You all made me go through 4 iterations before I stopped. We had FR, ant, dog, grasshopper, bee, FI, and snake. Okay? So we had frog, ant, dog, grasshopper, bee, fish, and snake. And we start now with FR being the smallest and the current. And then FR is going to compare against A. A is going to be, and I'll just do it quickly going forward because now we know the process. A would be the current, sorry, not the current, A would be the smallest, right? And nothing will be smaller than A. Nothing will be smaller than A. So you will switch FR and A, right? You'd switch FR and A. So what we'll end up getting is A, FR, D, G, B, Fi, and S, right? Now FR is going to be the current and the smallest, right? FR is going to be the current and the smallest, and we compare it against everything else going forward. the smallest that we will find is going to be the value of B. So you'll end up with A, B, D, G, F, R, F, I, and S, right? Now D is going to be the current and the smallest. And you search forward, and what is smaller than D? Anything is smaller than D here. G is not smaller, FR is not smaller, FI is not smaller, and S is not smaller. So you'll end up with the same thing. A, B, D, G, FR, FI, and S. G will be the current and the smallest, but when we make the comparison, we will notice that first FR will be considered the smallest, and then we compare FR and FI, and then find out that that is the new smallest, and S is not smaller than FI, so we'll end up with A, B, D, FI, FR, FI, FR, G, and S. And then we'll end up with C and S for the current and the smallest, and FR, FR, and G. G is not smaller, S is not smaller, so we'll end up with this same thing going forward, because at this point we've kind of gotten it to sort, right? But depending on the way that we write the algorithm, we might have 2 more iterations or 1 more iteration to just check the value of G against S. So which one of these does not appear while applying the selection sort algorithm, right? We have the value A, where we have ant, frog, dog, grasshopper, bee, fish, snake. That A appeared here, right? So B, ant, bee, frog, right? Ant, bee, frog, dog. So I see ant, bee, frog, dog. I'm not seeing B anywhere, right? There's no point at which we have A, B, F. So this one is a potential answer, but let's just check the others. Ant, bee, dog. So we have ant, bee, dog, and then fish, frog, grasshopper, snake, right? This is C here. This is C here, and ant, bee, dog, grasshopper, frog, fish, snake. This is D here. So the answer is B. The answer is B. Sorry, wrong thing selected. The answer is B. Okay, so this is one of those questions that you answer typically most questions within 10 seconds, right? You answer questions typically within 10 seconds in a multiple choice. But, this is one of those questions where you should take the time to go through, because it's very easy to make a mistake. So this question might take you a minute. All right. So A, D, and C, we ended up with that in. Yes, so and read the question properly, please. So assume that the list is sorted. When searching the sorted list, which of the following would be found most quickly using binary search? So now we have this last column here, search it, represented, and we want to search it. So we have A, B, D, F, I, F, R, G, and S. And which one would be found most quickly using the binary search? It's going to be the one in the middle. There's 3 before and 3 after it. This would be the middle value, because this would be the start and the end. So if we had to search for a value, the one that would be found fastest would be fish. I keep on choosing the eraser instead of the highlighter. So the answer is fish. C. Q is implemented using a one-dimensional array. Which of the following best describes the DQ operation performed using the array? So if we have a Q with a one-dimensional array, right, how do we want to implement the DQ operation? First, we have to check to see if the queue is empty and then return the first element in the array and shift the remaining elements up one place. That sounds feasible. Let's just look at the other answers. Return the first element in the array and shift the remaining elements up one place, right? Well, A is superior because A, of course, checks to make sure that the queue is empty, but we want the queue to be not empty. Okay, so C, check that the queue is not empty. Then return the first element in the array and shift the remaining elements up one place. And D just totally off by returning the last element in the array. So A and C could trip you up, but C is the answer here because you want to make sure that the queue is not empty. You have to have something in the array to return. Make sense?
Yes, sir.
All right, so read the answers carefully, people. Right, CXC out to trip you all up. Items 12 to 13 refers to the diagram below. This diagram is a what? Anybody?
A linked list. So D.
It's a linked list, yeah, because we have pointers referring to nodes, right? Which of the following operations is associated with the ADT above? The answer here is? Answer here is A. Thank you, Alexa. Right, insert. NQ is a Q operation, DQ is a Q operation, POP is a stack operation. Item 14 refers to this list. The target value is I. A binary search is employed. How many comparisons are made before we can conclude that the letter I does not appear in the list? So again, take the time to write it out in the exam. A, C, E, F, G, K, and L. This is going to be the start. This is going to be the end. So this would be the middle, right? I'm just going to put some index values up here. 0, 1, 2, 3, 4, 5, and 6. Okay, so 0 plus 6 divided by 2 is 3. So that's how we got the middle value. I. Is I after F in the alphabet or before F in the alphabet? I is after F. So I is after F. So now, because F didn't match up, right? We're only looking at this. We have G, K, and L. G is the new start. G is the new start. L is the same end. And K would be the middle value. Right? You compare K and I. I comes before K in the alphabet. Right? So, what is going to happen here? If we have the letter G, and G is going to be both the start value and the end value, right? G is going to be both the start value and the end value and the middle value. And what is going to happen is that we'll compare I with G. We will see that I will come after G in the alphabet. So you will end up with G being the end value and the start value being pushed to K. And if the start happens after the end, then you don't have anywhere that you could search. You can't search a negative space. So how many comparisons are made? We made a comparison We made a comparison with. We made a comparison here. We made a comparison here. And we made a comparison here.
B.
So the answer is B. Yeah. Okay. These are the kind of questions I know that you know your search, your binary search, but you might look at it in the examination and tell yourself, yeah, well, I know it, and you just do it quickly on the paper, or you try to do it in your head, and you make one too many or one too little. Take the time and write it out. Okay?
Yes, sir.
All right. I'm saying it, I'm saying it, and I'm saying it with proof now. You have a recording. So there's proof. All right. Take the time and write it out. All right. Item 15 refers to a segment of an incomplete algorithm for sorting an array list of size n using a bubble sort. We have a bubble sort, so we have bubble sort code. And I tell you all, I don't agree with learning off code. It's better you learn off how these things work. But you know, bubble sort and binary sort code and linear search and linear search and binary search are probably the only 4 pieces of code I would say you can learn off and know familiar. But it's always better to know the process. Because if you know the process, you can always move back out the code very quickly. Right? So we have some a bubble sort, and just to recap how a bubble sort works very quickly, if it is that I have 4 values to sort, 9, 3, 2, and 7, 9, 3, 2, and 7, and I want to sort this, how the bubble sort works is that I take the value of 9 and I compare it against what is next to it. If the value next to it is smaller, then I swap them. So I'll get 3, 9, 2, and 7. And then I hold on, I go to this value here, and I compare these two, 9 and 2. And if the value next to it is less than, I swap them. So I end up with 3, 2, 9, and 7. And I do the same thing with the last value, right? I'll end up with 3, 2, 7, and 9. And then because there's nothing to compare after 9, I start over at the beginning. So I end up with, I start off by looking at 3, 2, 7, and 9, right? So that was the first pass. And then I have to compare 3 and 2. 2 is smaller than 3, so I have 2, 3, 7, and 9. And then I could compare 3 against 7, right? Is 3 smaller than 7? Is 3 smaller than 7? It is smaller than 7, so there's no need to swap. So 2, 3, 7, and 9, right? And depending on how you write your code, you could have written it so that you know that this value doesn't need to swap. You know that this value does not need to swap, right? So you could probably stop here and freeze it right there. Understood? And you keep on doing that until, of course, your values are sorted. All right, so we know how the bubble sort work. We just had a quick little go through with the bubble sort. Right, we had a quick little go through with the bubble sort. And let's take a look at the code for it. So we start off with saying flag is equal to false for position, right? The size of the array is n. So for position 1 to n minus 1, do. If list at position is greater than list at position plus 1, then what do you want to do? We just did this, right? And of course, we're in a repeat until loop. So if position if list at position is greater than the list at position plus 1, if 9 is greater than 3, what did we do? Anybody want to help me out here?
So you could repeat that?
Right? We're looking at what did we do? We just did some activities in terms of swapping some values. Okay? We know that we're going until flag is equal to false or n is equal to 1. So what do we have to change inside here to know? Once we make a, we have to change that flag to true, because that flag is equal to false will tell us, okay, we went through a whole iteration and made no changes. And that tells us that the list is sorted. Or n is equal to 1, right? That would tell us that the list is sorted. But so one of the things that we have to do is change the flag to true. But the thing is that in all of these, we have flag is equal to true. So in all of them, we have flag is equal to true at some point. Okay, so that doesn't really help us here in any big way. But we have to know how to swap. We have to be able to swap a value. That's what the other thing that we did inside of here. So how do we swap a value? So if I have list at position pos is equal to list at position pos plus 1. So let's just say we go back to our example with the 9327, right? With the 9327. If this is pos and this is pos plus 1, okay, this is pos and this is pos plus 1, we're going through the code in A. Right? List at position pos is equal to list at position pos plus 1. So what did we do here? We said make this value 3. What happened there? We lost the 9. We lose the 9, we can't swap at this point. Because if we continue, temp is equal to list at position pos. If I have temp down here, temp is now 3. All we have is 3s. So this is bad code, right? That's bad code. So let's go back and put back our 9 there. Okay, let's go back and we put back our 9 here. Now we're checking B. Temp is equal to list at position pos. So temp is equal to list at position pos. So temp is 9. Right, so we do this. List at position pos is equal to list at position pos plus 1. So we take the value at pos and we take the value of position pos plus 1 and put it inside there. So this is 3. List at position pos plus 1 is equal to temp. Temp is 9. So we put 9 inside here. Is that what we did the first time? Yes. We swapped these two values here. So B looks feasible. Right? B looks like the potential answer. Let's just see if the others could work or if the others are garbage, right? Sometimes CXC make a mistake, maybe they put 2 answers inside here. I don't think that's the case here. Temp is equal to list at position pos. So this was 9 and this was 3, right? Temp is equal to list at position pos. So temp is 9 here. List at position pos plus 1 is equal to temp. We put a 9 inside of here. So that's bad business. So we know that this one is garbage, right? And the last one, the last one, temp is equal to list at position pos. So we put 9 inside here. List at position pos plus 1 is equal to temp. Put 9 inside of there is garbage again. So the answer in this case is B. You all understand how we work this out? You're not
Yes,
going
sir.
to
Quick
run out of
question.
time in the...
Quick question for you, Paul. How come they put it to n minus 1? Well, like because if you're
Well,
starting at 1 and you're going up until n minus 1, like how come they said n minus 1 instead of n?
because remember when we reach to here, right? N is going to be pos is equal to n1 to n minus 1. Oh, of a size n. Yeah, that looks like an oversight on their part. That should have been probably n minus 2. Right? Because yeah, because then you're going to get this value here, assuming that the array started at 0. But you see how they didn't start at 0 here? And this is the kind of funny thing about here, because at the previous question you had to assume that they start at 0. But in this case, we might have to assume that they started with the index values 1, 2, 3, and 4. You understand what I'm saying?
Somewhat, so I thought it would have been from 1 to n, but
Yeah, it's in this case, if the array starts at 1, then n minus 1 works.
okay.
Yeah.
Okay.
Right, yeah. So it's used to account for starting the array at 1. In the previous question, they started the array at 0. So it's just a lack of consistency on the examination council part. All right.
Okay, so
What I'm going to do is I'm going to give you guys a 10-minute break, and when we come back, we'll finish the rest of this paper. Right. So the rest of this paper shouldn't be that hard to finish, because the first section, the first 15 questions are programming-based questions where we have to write out and work out stuff like this. But the second part, it's a little more theory. So I'll see you all in about 10 minutes or so.